Today we're going to be recasting a nonlinear higher order ODE into a first order system of equations. This method also works for linear ODEs as well. The first thing you should always do is to solve for the highest order derivative. In this case, it's the third order derivative of y. So we get y triple prime of x equals 3, y double prime of x minus 2, y squared of x. Now we can write, since y of x equals y prime, y double prime equals y1, y2, y3. Notice that you will always have the same number of rows as your highest order derivative, so we have up to y3 and we have a third order differential equation. Now we can write then y prime of x equals y1 prime, y2 prime, y3 prime equals y prime, y double prime, y triple prime equals y2, y3, 3y3 minus 2y1 squared. And this is all equal to a multivariate vector valued function that we're going to call f. Notice that the last stroke here will always equal our highest order derivative, and that's why we solve for it at the beginning. Just make sure to write it this time in terms of y1, y2 and y3. Now we have initial conditions up the top, so we can't forget about them. So we can write y0 equals y1, y2, y3 equals 1, 1, 3. Now we could also go one step further and say that because f is made up of basic operations, such as the sum and product, then f must also have continuous partial derivatives on R3, and therefore using the fundamental theorem of existence and uniqueness, the initial value problem has a unique solution on some interval around the neighbourhood of x equals 0. Now let's do another example to get the hang of it. Here we have a second order nonlinear ODE, and just like the last time, we're going to solve for the highest order derivative. So we get y double prime of x equals the natural logarithm of y times y prime plus the square root of x times y. Now we write exactly the same thing as in the first example, only this time we have 2 rows instead of 3 because we have a second order ODE, so y is going to go up to y2. Now for this second part, our very last row is once again going to be equal to our highest order derivative, which is why we solve for it in the first place, but we make sure to write it in terms of y1 and y2. So we get the natural logarithm of y1 multiplied by y2 plus the square root of x multiplied by y1. And this is all equal to a multivariate vector valued function that we're going to call f. And once again, we have our initial conditions, so we can plug in x equals 2 and get y1 equals 4 and y2 equals 5. If you like this video, then please give it a thumbs up. If it helped you out, then please subscribe. I upload videos regularly on calculus, linear algebra, statistics, psychology, physics, as well as general university study hacks. And as always, thanks for watching.